Hello everyone, welcome to a new lecture from VLA for autonomous driving. We'll get started soon, but before that, can you just confirm in the chat if you can see my screen, hear my voice, and see me all right? Awesome, thank you. So in today's lecture, we'll be discussing about reinforcement learning in the context of the self-driving that we have been discussing throughout in this lecture series. In today's lecture, the only element that will be missing will be the language intent. We'll not be adding language intent because the lecture is already complex as is. So language intent is just an additional thing which we can add, but fundamentally understanding how reinforcement works in this context itself is a great thing for you to understand. So today we'll be looking at vision action models, not necessarily vision language action models, but action language is just an additional layer which we can add in the architecture. So one thing that I should just say from the start is today's lecture will have a tremendous focus on PPO, which is Proximal Policy Optimization. It's one of the most famous RL policies. There are other policies also. And there are several terminologies, several notations, and mathematical ideas to keep track of. So for you to fully wrap your mind around PPO, it will definitely take a very good effort. So two things you should ensure is just make sure that you have something to write on, like some notepad or something, so that so the terms that we are discussing, you can write it so that you can come back and you can have a look at it, of course. Second thing is pay very good attention because it's very easy to lose track of why did we introduce a certain terminology. And if some things are still unclear, just understand that if you just go through the lecture once more, if you watch the lecture video once more or twice more, your understanding will become better and better, because the longer the amount of time you spend on PPO, the better you'll understand the intuition behind it. In the initial, when you initially look at it, you will feel like you understand it, but then you will have knowledge gaps, which will create doubts. Then the more amount of time you spend on it, you will slowly, those gaps will become better, right? So just understand that there are a lot of mathematical notations and terminologies that we'll be discussing about. Without discussing that, it's very difficult to understand PPO, how it is. And towards the last part of the lecture, I will discuss about an assignment which I want to give you, which is training your own car in an environment called Meta Drive, so that you are training it based on vision input. There is also a reward function. And based on that, your train policy should be able to navigate that environment. That training is a little bit complex in the sense it takes a lot of time for training, which is the reason why that training we will not be doing it during the lecture. It will be an assignment so that you can execute it after the lecture. But we will set up everything that you need to reach till that stage. Okay, so far in this, if you look at the past lectures, we have discussed about vision action models were it's a CNN based vision embedding, and then it's used for action. That was pure behavior cloning. We also discussed about action chunking transformer, where there was conditional variational autoencoder and language embedding. In one of the lectures, we discussed about world models, and then we looked at how to connect the hardware TurboPy with your coding agent so that you can implement things fast. We also looked at how to run the vision action model and action chunking transformer in Isaac Lab. So these are the things which we have discussed so far. One more thing which is remaining in the next lecture would be using agent as a policy, using coding agent itself as a policy rather than using a trained neural network as a policy. So we will see that in the next lecture. But before that, I thought introducing reinforcement learning would be a very good fit to what all things we are learning in this lecture series. So in this slide, I'm just trying to explain what is PPO. I'm 100% sure you will not understand what is PPO completely from this. But the only reason why I'm mentioning this here right away is so that later, when I keep talking about PPO and when I keep talking about some of the terms, there is at least a minimum context. But I'm explaining everything in detail in the upcoming slides. But PPO stands for Proximal Policy Optimization. It was introduced by a team from OpenAI. 2017 was the year. So it's been quite some time, and there are other policies or other reinforcement learning policies that have been introduced afterwards, but PPO still remains as one of the most popular ones. So Proximal Policy Optimization. So we have to understand all these three terms. You will not understand what is proximal yet. We'll come to that. Policy simply means what is the model which results in your car driving? Your car has to take a decision. Which model is allowing the car to take that decision? Optimization is optimization of that policy's performance. That policy has to become better and better over time. So we will come back to this slide, and after a proper understanding of the PPO, then all these elements which you are looking at right now will be very clear to you, right? But I just wanted to say this upfront, although I don't intend to make you understand PPO right now this second. Now let's come back to what we have been doing so far. What we have been doing so far is something called behavior cloning, meaning there is an expert. An expert will collect training data. The actions of that expert will help you train a student such that the student can try to become as close to or as good as the expert, right? But one thing is that if you have an expert, and if the student is purely trained on expert data, the student cannot become better than the expert. Student will at best be only as good as the expert. Student will never be better than the expert. The reason is the training data, although we are performing augmentations, although we are trying to generalize the training data as much as possible, we are still limited by the fact that we are trying to optimize the loss of any neural network when we are trying to train the neural network so that the actions are like that of the expert, where the loss function is such that the loss is minimized when the actions mimic that of the expert. So there is an inherent problem with respect to expert-based behavior cloning. So this is where reinforcement learning comes into picture, where in reinforcement learning, the agent or the car can actually take actions which are different from what the expert showed. It can take different actions and it will get different rewards. And the more the number of times it does that, it can figure out what action sequences can result in better and better rewards. And it can be even in such a way that the reward can be, even higher than what the reward would have been if you calculated the reward for the expert actions. So that's the idea. So that's the power of reinforcement learning. And this is one of the reasons why you might have seen, AlphaGo beating, in the Go game, the AI could beat Lee Sedol, who was the champion at that time. And you could also see many other, even in Dota game, actually AI was beating world champions. That was because it doesn't matter what the expert is doing. Through reinforcement learning, you can take various actions as long as there is a proper reward function setup. That actions will result in a reward from the environment, and the increase or decrease of that reward will help us go in the right direction to maximize it. Then reinforcement learning is the broader term. PPO is the proximal policy gradient. It is one of the reinforcement learning frameworks. And in our case, we'll be using the PPO for a vision action setup where a car will be there. Car will be looking at the scene. So only the image will be visible. The image will look something like this. Let me just show you an example. So here I hope you can see the GIF. Can you see this GIF image? Okay, so something like this. So this is an example of the meta-drive environment in which you will also be training your agent. And here you can see that the agent is failing. Agent is directly going and falling down. But in an environment like this, where the input is a visual image like this, like 100 by 100 pixels or something like that, this is what you will be doing, okay? So in the previous sessions, we created image action pairs or image language intent action triplets. In our case, we will not be doing that. We will be doing something very different. So first, we will discuss about the general reinforcement learning loop. What is agent? What is environment? What is state, action, reward? What is return? What is discount, exploration versus exploitation, etc. Then we will be looking at more specific terms like policy, value, advantage A, then the reinforce. This is a very old algorithm. We'll discuss about that. Then we'll also discuss about ideas called actor network and critic network. And then finally transitioning to PPO, Proximal Policy Optimization. In PPO, there are a few different terms that we'll be looking at. Clipping, generalized advantage estimation, entropy, KL divergence, etc. In the last part, we'll discuss about the vision PPO racing tasks that you have to execute as part of this lecture homework. All right. Okay, there is a question. Is it coming up going over all enumerations in the enumeration tree in PPO algorithm? I will discuss that, Pratik. We'll discuss all of this through the lecture. So first, let's go through what exactly is reinforcement learning versus behavior cloning. So in behavior cloning, you drive the car, you collect the data. So you have a collection of state action pairs. What is state? State is the RGB image in our case. In self-driving car case, we have a bunch of RGB images. Those are the states. States meaning what is the current situation. Action is corresponding to that state. What action, driving action are we taking? Are we going ahead or are we going left or are we going right? In the case of TurboPy, it is XY, VX, VY, and Omega. There are three actions possible. So what would be the VX, what would be the VY, and what would be the Omega? That will be the action. And then supervised loss calculation, meaning a neural network will try to predict actions corresponding to states and will try to match that action with the expert action. And that will be the loss function. So that is the supervised loss calculation. And the policy network is simply the trained neural network. So whenever we mention policy, imagine a neural network, that neural network that is able to make an action prediction. So the neural network will predict an action for a new state, and then that action will result in the change of the state and so on, right? So, but the neural network is trained such that it minimizes the loss, where loss is the difference between predicted action and expert action. That is the behavior cloning. In reinforcement learning, we don't do that. What we rather do is we have an agent, which is like the car. We have an environment. Environment can be the real world environment. It can be a simulated environment, whatever. Action is what the car is doing. Is it moving forward, backward? Is it going left, strafing? What the action is. And reward is explicitly defined reward function. So if you remember from the world model lecture, we had rewards based on checkpoints. So in the square path, we had a bunch of checkpoints laid out throughout the track. So that was the reward. Or we can say for keeping forward velocity greater than 20 miles per hour, put this much reward. For turning slow at the corners, as long as speed is less than this much kilometer per hour, put this much reward. As long as you are driving centered in the road, have this much reward. As long as the orientation or heading of the car is same as the orientation of the track, have this much reward. So you can have various reward functions adding up to produce a net total reward. And then what is the state? The state will be whatever the agent is seeing from the environment. Agent will see if there is a camera, that camera input will form part of the state. If there is camera plus other sensors, all that will form part of the state. Okay. And then a policy network will learn to maximize this reward. That is ultimately what it does. The policy network will become better and better and better, such that the reward is maximized. We are not directly comparing the action selected by the policy with an expert action because there is no expert action available in the first place. All right. Will it be able to do avoid obstacles with reward functions? It's by Rajesh. Yes. If we set up the reward function such that obstacle avoidance is also part of the reward function, it can do that. Basically, at the end of the day, it's about reward function. Think about it. When you are playing a game, computer game, you figure out how to play the game because if you take certain actions, the game treats you better. It gives you reward. Otherwise, it gives you punishment. So you learn what path to take if it's like a exploration game or something like that. Just like that, the agent, if a reward function is set up in the best possible way, it can basically do any task, right? All right. So that is the basic of reinforcement learning. In behavior cloning, you have image action pairs, which results in supervised learning. But in reinforcement learning, the actions can be anything, and the reward gets the policy gets better and better over time as it goes in the correct direction of reward. The Pratik is asking, am I correct? The action is moving left, right, pushing brakes, etc. Yes, that is the action. So in the example that we are discussing in meta drive, there are two actions. One is the angular position of the steering. Second is the throttle. Throttle is how much are you applying the accelerator. Angle of the steering decides in which direction the car goes. So angle and throttle. There is one more question. Can we add or modify reward functions after the model is trained? Or each time we update these reward functions, we have to do training? That's a good question. Technically, there is nothing that prevents you from modifying the reward function later. Then the only question will be, if you modify it abruptly, is it useful to have the policy which you trained up until that point, or do you start from scratch? That's the only question. But technically, there is nothing that prevents you from slightly modifying the reward function after you have a trained policy. You can think of it almost like fine tuning, right? You realize that, okay, you initially the environment was a little bit simple. So you kept a simple reward function, then you trained the policy. Then the environment became a little bit more complex, which means the reward function is also having additional terms. And you realize that now I have to again train the policy, but instead of now starting from scratch, you start from where you left off. You can do that. Okay. One thing is the training will take a lot of time. So even the basic training, which we are going to discuss in today's lecture on CPU, it will take 3 to 5 hours of time, which is the reason why we will not be able to do it in today's lecture. The training we won't be able to do. We'll do it separately, but that's the basic idea. Now let's discuss some basic terminologies. The state, action, reward. So state in our case is RGB frames. And here when it says 4 stacked frames, it means you're looking at the last 4 frames. Last four frames as in, you look at the history of 4 frames to predict the next frame. Action, as I said, is steering or throttle, steering angle or throttle. Reward is how much reward are we getting for the corresponding action. Agent is the car, environment is the virtual environment in which the car is there. In our case, it will be like a meta drive simulator. There is a GitHub repo called meta drive. You can just search meta drive GitHub. So it's like a lightweight driving simulator. When I say lightweight, it's not as lightweight as the simulator that we were using in the first 3 lectures. That was even more lightweight, but this is really good, a lightweight driving simulator. Just check this out. So we'll be using this simulator during the exercise, which you will do from home. Then, okay, this we already discussed. So what the environment will return is, it will return the next state. It will return the reward corresponding to the transition which you did by taking the action. And then there will be a done flag. And the definition of one episode is after you reset the starting of an episode, and you are going till the terminal state. Terminal state could be the following. In our case, we have a road. It's like a sky road. If you go out of it, it's as if you are falling down. That is a terminal state. The other terminal state is you reaching the end of the road. So those two are the terminal states in our case. But the terminal state can depend on what kind of environment you have. Maybe hitting something could be a terminal state. Maybe taking, ending up in certain state, like you are stuck somewhere. That could be a terminal state. So the definition of terminal state clearly depends on what kind of environment you are in. The definition of what is an episode is starting from reset till reaching the terminal state. That is the definition of one episode. Now, just have a look at this term. This term G is called as return. So please note this down. If you want to write it down somewhere, just write it down. Return equal to G. Okay. So whenever I say return in future, I'm referring to this G. So what is this G? This is a discounted return considering current action as well as future actions. So for example, if I were to consider bunch of actions starting from time step t equal to 0, t equal to 1, t equal to 2, t equal to 3. So I'm taking at each of these time step, I'm at different states. And at each of those states, I'm taking a particular action. As a result of those actions, I am getting rewards. So let's say the first reward was 0.5, then I got 0.7, 0.4, 0.9, 0.6, etc. Now, if I were, and these are, let's say, and now you are sitting at state t equal to 0, and somehow you had a way to calculate based on your policy. If you executed the actions, you will end up getting these rewards in the future time step, future 4 or 5 time steps. If that was the case, there is a way to calculate the total return resulting from this entire episode. The total return resulting from the entire episode G for the time step T is RT, which is the return from the current step, plus gamma times RT plus 1, which is the return from the next step, gamma square multiplied by RT plus 2, and so on, gamma raised to T. multiplied by RT. Now, this is very similar to the way you calculate something like net present value. For example, it's very, let's say somebody gave you $100 today versus somebody gave you $100 5 years later. Your value of $100 is greater today than it was given to you 5 years later, which means the $100 which is given to you 5 years later has to be discounted. Somehow it has to be multiplied by a discount factor to calculate its net present value. So this is almost like calculating the net present value of all the future actions, right? So GT and gamma value will be always between 0 and 1. If it is 0, let me ask you a question. If gamma was 0, are you giving importance to the future or are you giving importance to the present? If gamma is 0, what it means is none of the future rewards matter. The only thing that matters is the present action which resulted in present reward RT. What if gamma was equal to 1? If gamma was equal to 1, you are giving equal importance to all rewards which resulted from all the states, not just the current state, but also all the future states, right? So typically, the gamma value will be somewhere between 0 and 1, so that it's neither too small nor too big. I mean, it depends on really your environment. But the gamma will be such that there will be, the current reward will be given full weightage, but the future rewards will be discounted. So gamma will be let's say 0.9. Gamma square will be 0.9 multiplied by 0.9, which is like 0.81. And gamma raised to, let's say, 100. If gamma is equal to 0.9, 0.9 raised to 100 will be a very small value. So what that means is, even if you get the same reward after 100 steps, it doesn't matter because the future is uncertain. So when I calculate the return, I should discount that heavily because that reward I am getting after 100 step, which I'm not even sure if I'll reach there. So I'm just discounting it. So basically, GT is if you were to simulate somehow the future actions in your mind, meaning in a simulation, and if you were to get rewards corresponding to each of those actions, how do you calculate the net present value of all those rewards? That is what is GT, and the plain English term for GT is return corresponding to time t. So please note this so that this will be referring to in the future. Then there is the concept of exploration versus exploitation. So exploration versus exploitation is that if let's say, and by the way, policy is a probabilistic model in the sense that if you give the same input, the policy will not give the same output. Policy will pick from a probability distribution, just like a Gaussian. So if you have a Gaussian curve whose mean is 0 and standard deviation is 1, if you sample from that Gaussian 100 times, those numbers will very likely be somewhere closer to the mean, right? It will be closer to the mean. Many numbers will be closer to the mean. Few numbers will be far away because standard deviation is not 0. So when you sample from a probability distribution 100 times, you will get a bunch of numbers, but they will be distributed along that probability. Similarly, your policy for the exact same state, for the exact same observation, which is like the exact same image which the car is seeing, the action will be dependent on what we are picking from a probability distribution. And how that probability distribution is arranged is depending on basically what the policy is. So policy is essentially a probability distribution from which you can sample an action corresponding to a particular state. Okay. Now, exploitation means you always pick such that you are at the mean of the probability distribution. An example is, if you have a probability distribution whose mean is equal to 1 and standard deviation equal to 0.5, you always pick the highest probable outcome, which is outcome where mean is equal to 1. Exploration is, you don't always pick the action such that you are you're picking from the peak of probability distribution, but rather you're picking anywhere from the probability distribution. So such that you may be picking an action which is suboptimal. So in the current time step, you may pick an action which is suboptimal, but we don't know, right? Maybe that will result in a better future reward or better overall return. So exploitation means in the current time step, if you are sampling from the probability distribution, you sample from the mean, sample at the mean. Exploration means you are sampling anywhere from the probability distribution. Just two terms. I mean, we will keep using exploration versus exploitation, but just by looking at the English language, you will understand. Exploitation means you maximize the immediate reward. Exploration means you don't care about maximizing the immediate reward. You don't care about taking the action which maximizes the immediate reward. That is what exploration means. And that is what I just discussed, deterministic policy versus stochastic policy. So these deterministic policies are almost never used. Deterministic policy means for a given state. So let's say the state is such that the car is seeing a bridge or something like this. That is the state. The reward is always deterministic. As long as the state is the same, reward is the same. But I mean, the action is the same. But that is not the case with stochastic policy. Stochastic policy will have the same input, but since you are sampling from a probability distribution, you will get different actions when you sample different at different instances. So P of steer is the probability distribution for the steering action. P of throttle is probability distribution for the throttle action. So now the action is a pair of two numbers where this is the action corresponding to steering. Maybe it could mean 0.1 to 12% throttle, and 0.71 means 71% or 71 degree. It can mean anything. I mean, it depends on how you scale it. But 0.12 is a number which you will get by picking from this distribution. 0.71 is a number which you will get by picking from this distribution. So there are two Gaussians, and when you plot two Gaussians on x and y axis, you can get a two-dimensional normal distribution or a diagonal normal distribution. So that's the difference between deterministic policy and stochastic policy. Just to be clear, we are never discussing about deterministic policy. In our case, for the same input, we will not get the same output always. There was maybe one model in which we discussed something similar in the past lecture, where for the same input, we will never get the same output. Which was that model, if you remember? In which model are we? Because usually, if you think about CNN, if the weights and biases are all fixed, why would you get a different output when you input a different image? You will always get the same output. I mean, the output is going to be exactly the same if weights and biases are unchanged. If you input the same input image, the output prediction, softmax or whatever prediction is at the final output, it will be the same. And we also discussed that the policy is essentially going to be a neural network, which means in which of the models that we discussed earlier, can we expect different output for the same input? Think about it. Diffusion model is a very good example, or even the conditional variational autoencoder part of the ACT. Basically, there what we were doing was, we were not directly predicting the output. We were predicting a mu and a sigma. So mu and a sigma, which defines a distribution. Then from that distribution, whose mu is the predicted mu and whose sigma is the predicted sigma, we were sampling something. So because we are predicting mu and sigma, and then we are sampling from that distribution for the exact same input, even though we will get the exact same mu and sigma, we will not end up getting the same output because we are sampling from that mu and sigma distribution, right? So the conditional variational autoencoder part of action chunking transformer is a good example of a part of a neural network where even if input is the same, output will not be the same. Whenever we sample from a probability distribution, that will be the case. Same thing applies here, okay? Okay, let's look at this question. A student trains a policy with gamma equal to 0.5 to make the agent focus on the near term. The agent learns to lurch forward at every step and then immediately fall off the sky bridge. Why? So think about it. This is like if gamma is 0.5, gamma square will be 0.25, gamma cube will be even small, which means when the return G is calculated, it has, the future actions have very little influence on the return. And we'll see later, but essentially what that means is the model is not really prioritizing what the future actions are. You don't care about future actions because anyway, that reward corresponding, whatever the future action be, the reward corresponding to that future action is getting discounted by a factor like gamma raised to n. And if gamma is a small number, gamma raised to n will be an even smaller number. So it doesn't matter what your future action is for calculating the return. It will primarily depend on the current action. If gamma is a small number, it will primarily depend on the current action. So because of that, the discounted return, what is the discounted return? The future actions will be applied a discount. So this will not allow the model to see through the future. It will only look at the current, primarily it will look at the current action. So if you want it to look at the future action, you have to keep the gamma value a little bit higher. Now let's discuss some terms in the next few slides. Policy, value, advantage. Then there is one more term called generalized advantage estimate, GAE. We'll discuss all of that. Please pay very good attention because there are several terms that we have discussed now. We discussed policy. We discussed state, action, reward. We also discussed return. Reward is different from return. Reward is for an individual step. Return is for all the future steps. Return is denoted by G. Reward is denoted by R. Okay. So please remember so far, whatever we discussed so far. Now there is a concept called state value. State value is nothing but if I am at a certain state, and from that state, let's say I were to follow the policy. So I have a trained neural network. From the current state, I will follow whatever my trained policy is suggesting until I reach the terminal state. And like that, I will do 1,000 times. So just think about it. From the current state, so let's say the car is here. Car is seeing something. Based on what the car is seeing, my policy will tell me, take action such that throttle is equal to this much, steering is equal to this much. I will take that action. Then my state will change. Then again, my policy will tell me what to do. Then again, it will tell me what to do. Like that, I do until terminal state is reached. This is one episode. Like that, let's say I generate 1,000 episodes. In all the cases, the current state is the same and the policy is the same. Do you think the path the car will take in all these 1,000 episodes will be the same or will it be different? So I'll repeat my question. You have a policy network. Based on the policy net, and I have a given state. Let's say the current state is this, where the car is. And if I were to simulate 1,000 different episodes where car is starting from the current state and it is it is operating till the terminal state, or let's say it's operating for 1,000 steps, whichever comes first. If I run 1,000 such episodes, my policy is exactly the same. My initial state is exactly the same. Do you think the path which the car takes will be exactly the same? The path will not be exactly the same. Because the policy network is deterministic. So policy network will sample from a distribution to say, hey, this is the action that you have to take. When you sample a large number of times, there will be some averaging effect, of course. So on an average, the car will be taking a certain path. But around that average path, there will be some other variance also. Right? So that's what we are trying to do. We are trying to see what paths will the car take on an average if I were to follow the policy. Now the value V of S, so this value is called state value, is the definition of that is, given the current state, if I were to simulate thousands of such episodes using the same policy, what will be the average return that I will get? Because for every simulation of the episode, let's say I'm simulating 1,000 future time steps, I can calculate a return. What is return? Return is G. For every episode, I can calculate the return. How do I calculate the return? RT plus gamma times RT plus 1 plus gamma square times RT plus 2, so on, right? So like that, for future 1,000 steps, I can calculate the G. That G I can do for all the 1,000 simulations that I'm doing. And then if I average all of those out, I will get an average G or expectation value for G. What it is telling me is how good is the current state is, irrespective of what action is being taken. Because I'm not saying in the current state, take this action. I'm just saying in the current state, follow whatever the policy is saying and execute these many number of steps and do that thing 1,000 times. If I do that, you will have 1000 returns, meaning 1000 G values. And if you average all of that, you will get a number. That number is called state value. The higher the state value is, it means irrespective of what actions you are taking in the future, you are in a good state. If you are in a lower state value, it simply means where you are in the current path, you are in a bad position. Just to reiterate, if state value is higher, it means if you are driving a car, okay, think about it. If the car is at the start of the track, okay, if the car is at the start of the track, do you think the state value will be high or low? If you are at the start of the track, will the state value be high or low? Think about it. It's what is state value? Is this a good state to be in? Is the start of the track a good state to be in? No, because at the starting of the track, your overall reward will be very low. Because here we are rewarding the car for going from the start of the track till end of the track, right? And the reward function will be such that if the car manages to reach there, its reward will be very high. At the start of the track, so a car to be in a position where it is somewhere far away from its high reward terminal state, it's not a good place to be in. So if, however, the car was closer and closer to, so let's say the terminal state or the finish line of the car was a high reward point, then it's good for car to be somewhere closer to that. So if you were to and the logical reason for this is, if you were to think about it, let's say you have a train policy, the policy is probabilistic. How likely is your car to fail reaching the finish line? The likelihood of the car to fail the likelihood of car to fail to reach the finish line will be highest when the car is starting from here, don't you think? Because from here, the car has to traverse a lot of distance because there are a lot of actions to take. So the failure likelihood is very high, which means if it fails or falls down, there will be a huge negative reward associated with it. On the other hand, if the car is somewhere here, and if this is the finish line, and if you apply the same policy, the car will likely reach the finish line because there is only little distance to cover, which means the value of the state, value of being in this state is very high compared to value of being in this state. Because from this state, it is not at all guaranteed that you will reach the finish because there is a lot to cover. But from this state, you are closer and closer to finish. So it is much better for you to be in this state rather than in this state. So it just, the state value is simply an estimate of how good the current state is. Okay. So that is one term. Just to clarify how the state value is calculated, let me just write it down over here. So let's say I am at state ST. And let's say I am performing the calculation for the next 100 steps. Okay. So this is my iteration number 1. I went ahead 100 steps and I reached ST plus 1. And to denote that this is my first experiment, I'll just write it using something like this. So from ST, I reach ST plus 1, and this is my first iteration. Now, corresponding to this, I would have not ST plus 1, sorry, ST plus 100. Because I traveled 100 steps, and this is my iteration number 1. So if I travel 100 steps, there would have been 100 rewards. And based on those 100 rewards, I can calculate the GT. So corresponding to this, I will have a GT1. Then I will try another one. I'll try another experiment where I will try to reach ST plus 100. But this will be my second experiment. This will result in GT2. Will GT1 and GT2 be same, exactly the same? Never. Why? Because GT is equal to RT plus gamma times RT plus 1 plus gamma square times RT plus 2, so on. And how do you get R? How do you get reward, first of all, or any of these R's? Is it deterministic? No. Why? Because reward is coming from the environment based on state and action. And action is resulting from the policy pi. So because pi is deterministic, your action will be different. Because pi is not deterministic, your action will be different. And because your action will be different, the environment will give you different reward. And because these rewards are different, your GT1 will be different from GT2. Your GT2 will be different from GT3. And let's say you do this 1,000 times, you will have up to GT1000. Now, what are these GTs? These GTs are expectation value. And when you take an average of this, that is basically an expectation value of G for a given state, right? Because from this given state, I tried to follow my policy, and policy is probabilistic. I tried to follow my policy to reach till, let's say, terminal state. It gave me GT1. Then I tried it again. It gave me GT2. If I tried infinite times, theoretically, if I tried infinite times, it gives me some sort of expectation value. I hope you know the term expectation value from a probability, but basically think of it like an average. It will give me an expectation value for GT. And this averages of these, and G is what? Return. G is called return. R is reward. Please don't confuse. So G is equal to, return is equal to G. Reward is equal to R. So if you do it these many number of times, you can get okay, what is the expected value of return that I can get from this state, irrespective of what action I take, because action is dependent on the policy. Okay. So that was the first term. And in general, at least in this example, the state value will be higher if you are closer and closer to finish line. If you are earlier, you may reach a terminal state sooner, and then you will get no further reward. Now there is another term called Q. Q is the action value. So what this says is, there is one more term called Q. Q of a given state ST, and it's also a function of a given action. So if you look at V is just a function of state. The state value is only a function of state. It is not V of ST, AT. It's not a function of action at a time t. It's only a function of state at time t. So this is not the case. This is the case for value, state value. However, for action value, so this is state value. This is action value Q. It's Q of ST, AT. So it is a function of both state as well as action. So what this says is, if my car, let's say this is my finishing point, and my car is coming in, there is like a junction. And let's say two cases. In one case, the car is here. In another case, the car is here. Okay. Now let's talk about, and let's say this is state 1 and this is state 2. And let's talk about V of S1 and V of S2. In which case do you think the V will be higher? Is V of 2 greater than V of 1, or is V of 1 greater than V of 2? The value will be higher in state 2, correct? Right. So V of S2 will be greater than V of S1. But now let's look at another one. From this point, because the car is at a junction, it can go left, it can go straight, it can also go right. All right. Now, the definition of Q of ST is, if in the current state, if I take any particular action, so let's say the only 4 actions are available, let's say forward, backward, left, right. What is the value for all the future steps? considering all the future steps, if I take one particular action. So for example, this you can think logically. What else is Q of S2 given? So I'm giving you two options, Q of S2 given right and Q of S2 given forward. Which one will be higher, the first one or second one? Which value would be higher? Q of S2 comma forward has to be higher, because in the immediate current step, I will take forward. So the way it is defined is, you are in current state, let's say S1, and you try to go to state S2 through action number A, or you try to go to S2 through action number B, or you try to go to S2 through action number C. Let's say only three actions are possible. So action A, B, C, you are trying to go from S1 to S2 through either of these actions. Once you reach here, once you reach the state number 2, then you try to go till the terminal state by following the policy. Once you reach state number 2 via action number B, maybe I should not call it state number 2. I should, yeah, that's why I'm calling it as state 2A. So state 2A means you reach the state 2A through the action A. 2B means you reached 2B through action B. The starting state was 1. And once you reach this 2A, 2B, or 2C, you simply follow what the policy is saying. The policy will say from this state, take this action, this state. So this is now probabilistic. You take the policy to reach till whatever the terminal state is, right? And then if you traverse this path, you will have a GT. If you traverse this path, you will, and let's call this as GTA. If you traverse this path, you will have a GTB. And if you traverse this path, you will have a GTC. So Q of S1 comma A will be equal to GTA. Q of S2 comma S1 comma B will be equal to GTB. Basically, what is the value, what is the return that you will get, provided you are picking action A currently, and then for the rest of the actions, you follow the policy. If it is Q of S1 comma B, what is the value that you will get, provided you pick action B, then after that you follow the policy. And same for C, right? And there is difference, right? So the difference between that and the previous scenario is, here we are never picking any action. We are always saying always follow the policy, always follow the policy, always follow the policy. Here we are saying first take action A, then follow the policy. Then we say first take action B, then follow the policy. Then take action C, then follow the policy, right? So there is a difference between these two. So the first one is called state value. Second one is called action value. And you can see that state value is agnostic to action. State value says, don't pick the any explicit action, pick the action based on the policy. Action value says, pick a particular action right now and see if you were to follow the policy afterwards, what would be the total value, right? Okay. This is just a definition. We'll come to see where all of this is finally being used. Let's go back. Actually, can you hear me? My screen is getting stuck, I think. Just give me a second. Sorry about that. My computer got stuck. Anyways, let's go back to where we left off. You can see and hear the screen, right? See the screen and hear me, right? Okay, awesome. All right. So this is the difference. So just read the sentence. If I am at SB, then on average, this is a decent place to be. So that says the state B is a good state to be in. Then the Q of S comma A is if I am at state B, and if I specifically take an action of turning right, my outcome is great. So that is what Q says. So V says how good the state is. Q says for a given state, how good the particular action is. Then there is one more concept called advantage. Advantage is nothing but the difference between Q and V. Now think about it. The difference between Q and V conceptually is how much better is this particular action than the on an average. I hope you get that, you're understanding that. So just to clarify, Q tells me how good is this action, followed by following the rest of the policy for the rest of the actions. Whereas V tells, don't pick any action ever, specifically follow whatever actions policy is telling you. Now, for whatever reason, for the current state, let's say Q of S comma A minus V of S, if this quantity is positive, advantage, so the term is called advantage. It says taking one particular action in the current state is actually better than on an average blindly following the policy. That's what the advantage term says. So if we go by that logic, okay, in which case do you think advantage would be, or to put it in a different way, okay, out of these options, okay, it's obvious that the advantage will be higher if the value of Q will be higher. But if advantage is a positive number, what does it tell us? In plain English, if advantage is a positive number, what does it tell us? Advantage is the difference between Q and V. If advantage is a positive number versus negative number. So if advantage is positive, it means Q is greater than V for a particular action. Q for a particular action is greater than V. V is the average of the returns considering all the possible actions, considering the same policy. Whereas Q is for a particular action, calculate the return reward, then also follow the policy for rest of the actions and then calculate the return, right? So if Q is greater than V for a particular action, it means that taking that particular action at that particular time is better than just blindly following what the policy is saying. That is what the advantage term is saying. So if you plot the advantage graph, there is one nice graph over here. So let's say you have three possible actions: left, right, and straight. Left, straight, and right. Three actions. This blue line is what? This blue dotted line is representing Q or V. It is representing V because V is agnostic to action. State value is only dependent on the state. Current state is, let's say, SB. You are in state number B. For that state number B, you can calculate a value. And let's say the value is 61.6. It is the return, it is the expected value of return corresponding to that state. Then in that state, three actions are possible. You could either go left and then follow the policy, go straight and then follow the policy, or go right and then follow the policy. And let's say going right resulted in a return value of 48.2, which means the advantage is a negative number. Can you tell me a scenario where this may happen? Why would the just next immediate action result in such wide range of Q numbers? So Q of S comma A is such wide numbers. in this case, tell me a scenario where taking right results in such a low value of Q. It can be that turning right resulted in a collision, which resulted in very bad reward. Or it can be that turning right resulted in falling down from a cliff, which will result in very bad reward, right? So this one action can result in very bad reward because immediate to that action, there is some state change. And corresponding to that state change, there is a high reward or low reward. We don't know. So this advantage, which is the difference between this bar graph height and the dotted line height. So this green color curly braces say, okay, there is an advantage of 3.4 for this particular action at this particular state. For this curly bracket says there is an advantage of 9.9. So remember this advantage term. We will come back to it again when we discuss how this whole thing is set up. Okay. So just to reiterate, three terms we discussed: Q, V, Q, and advantage. V is the state value, Q is the action value, and A is the advantage. Advantage tracks how much better your particular action is compared to your policy-mediated average action. Now, what we are trying to do is we are trying to maximize some sort of reward or some sort of return. So return G is an index of how good my actions are. Because if return is higher, the higher the return, the higher the current action, or the better the current action and better the future actions, right? Because GT will be high only if current reward and future rewards are high. So somehow we want to maximize the value of G. So, and how do we get the G? We have a neural network also called as policy. That neural network has a bunch of weights and biases, which is called as theta. Then that neural net and pi theta simply means pi is the policy, theta are the weights and biases, which are the parameters. So pi underscore theta or pi with a subscript of theta, simply, if you see that, simply think of NN for neural network. Neural network as a function of its weights and biases. Actions are a result of what prediction the neural network makes. So the neural network, which is pi, will make a prediction corresponding to a state. That prediction will result in an action. That action will result in a certain trajectory. And that trajectory means you are reaching the next state. So from state ST, you will reach ST plus 1. And based on that, you will get a reward. And if you repeat this many number of times, you will get all the future rewards. And based on that, you can calculate a return. Your goal is, how can I modify the policy? Or rather, how can I modify the policy weights through neural network training such that my overall return can be maximized? That is the end goal, okay? So the this neural network which predicts the policy, which predicts the action, has a bunch of parameters. How do I change the parameter weights and biases? Should I increase this one? Should I decrease that one? How do I do that so that my expected return is maximized? That is the problem that we are now going to solve. Okay, this I already discussed. So this J of theta is basically the return function. So J of theta you can think of exactly like G, which is the return. Okay. So what we want to do is we want to find the local or global maxima of J of theta. So now when I say J of theta, think of return function, return which was G. So but here we call it as J of theta because we need a different notation to show that now you have a neural network which is predicting a G which is dependent upon the neural network parameters. So if you had a landscape of G, or if you had a landscape of a return value corresponding to different neural network parameters, what you want to find is the global maxima of that G. Because when you reach the global maxima of that G, you will achieve maximum return. So for that, what you want to do is you want to ascend, or you want to move in such a direction that your gradient of this J is positive. You are going in a direction of positive gradient of this return landscape, so that you are trying to reach at a higher and higher position of that return landscape. Now you will think, where did this equation come from? how did I get AT multiplied by gradient of logarithm of pi? So pi, pi is the policy, logarithm of policy. This is gradient of logarithm of policy. AT is the advantage, and sigma over T means you are summing over different steps. There is a very relatively simple derivation of how you go from J of theta to gradient of J of theta, and how do you reach at this particular expression? But it's not worth it discussing right now because it will consume 15 minutes. It's not difficult to understand. It is possible to understand. I will share you a nice PDF showing the derivation of this. But just understand that the gradient of your return is a function of, obviously, the gradient of logarithm of policy. It's also a function of the advantage, meaning if the advantage is positive, it's a good thing. You can go in the direction of positive gradient. If advantage is negative, it's not a good thing for that particular time step. And you know what will happen? Is this a shortcut to calculate faster? You mean this equation? It's not a shortcut. It's just it's a result of mathematical derivation. The reason why it said approximate is because in the original equation, instead of AT, it is GT itself, which is the return itself. But this is also a good way to approximate. We'll come back to it. But this algorithm of how you identify the gradient of your policy and how do you change your policy such that this return is maximized. It is called, that equation is called as reinforce, or that framework is called as reinforce. And it was a very old framework. If I'm not wrong, it was, I think, proposed in 1997 or something. It's very old. It's not used right now, but there are a few good things here. This graph, what this shows is, as I mentioned, policy is nothing but it's a probability distribution. And policy is what? Pi of theta. And what is theta? It is the neural network weights and biases. So when pi of theta, that theta itself is changing, your probability distribution will change, right? So when your neural network is trained, the policy, the probability distribution from which you will sample an action will be completely different. So what this graph is showing is, the original policy was this before a policy updation step in the neural network. And after you follow the step, the policy will get updated. Policy will be something slightly different, meaning it will be a different distribution. It's just like thinking, okay, I think this is the probability distribution from which we can sample an action. But then after training, you're saying, oh, actually, I have to modify the distribution a little bit. The mean has to be shifted. The standard deviation has to be reduced. And there has to be a skew. So if I do all of that, I have a better policy probability distribution, and that results from neural network training. So this policy update visualization is nothing but after neural network training, what will happen to your the probability distribution from which you are sampling your action. Okay. So reinforced algorithm simply does this. It says for every given time step, you calculate the advantage and you calculate the logarithm of gradient of the policy pi. If advantage is positive, it's a good thing, meaning it promotes the algorithm to pick that action more and more. If the advantage is negative, it does not promote the policy from picking that action. Why? Because if advantage is negative, the contribution of that to the gradient of J is also negative, which is not a good thing, because then you will not be able to maximize the return. If advantage is positive, then it's a good thing. So if advantage resulting from a particular action was positive, it positively contributed towards the gradient of J, meaning you are now able to go in the direction of maximizing the gradient, right? So this formulation inherently allows you to find actions at different states, which will help you maximize your GT. Okay, there is a question here. AT advantage does not account for the variance. Are you talking about the variance that is there in the actions? So variance is inherently part of the pi, the policy itself. When you are sampling from the policy, whatever variance is there in the policy's probability distribution, it is already coming in Q, it's already coming in V, which means when you calculate A, which is Q minus V, it's already coming in that, all right? But I think there is another variance which we have to discuss. We'll come to that in a moment. Okay, so just to recap all the things that we discussed. We discussed about state, action, environment. We discussed the difference between behavior cloning versus reinforcement learning. We discussed about the difference between stochastic policy and deterministic policy. Then we discussed about state value versus action value. State value is for all possible actions. It's action agnostic. Action value is specific to an action. Then we discussed about advantage, which is the difference between action value and state value. Then we discussed about the basic neural network framework, which wants to maximize the return. And then this is the gradient of that return, which can be formulated in an approximate fashion in this equation. And this is called as reinforced. This is still not PPO. PPO comes in a little bit. Okay, there is a simple question. A policy has V of S, which is value, state value corresponding to the state S is equal to 50. And action 1, which will result in Q of S comma A1, which is the Q, which is the action value for the state S and action A1 equal to 65. And Q of S comma A2 equal to 45. What does the policy gradient do at the state? Policy gradient is gradient of J. What does it do among these options? So what it will do is, if your advantage is positive, those actions are favored. If advantage is negative, those actions are less favored, right? And look at it. When is advantage positive? Advantage is positive is Q is greater than V. So here Q is 65, which is greater than V, which is 50. Here Q is 45, which is less than 50. So the advantage corresponding to action A2 is negative, and advantage corresponding to action A1 is positive. So if advantage is positive, it results in a positive gradient, which means the probability of the network will favor picking action A1 more corresponding to state S compared to picking action A2 more. So the network will change the weights and biases in that direction. Now let's talk about the term or the idea of actor-critic. Okay, that is the last thing which we will discuss before jumping into PPO. So we discussed reinforce algorithm and now actor-critic. So reinforce, actually not 1997, 1992. So it's a very, very old idea. The reinforce algorithm was basically finding the gradient of the return. Then actor-critic, I think there is a better slide to introduce actor-critic. I don't need this slide. Actor-critic is simply this. There is an actor head. So actor means the head which performs the action, meaning it predicts the action. So actor head will predict an action. Critic head will predict the value V. Okay. So just all of this will be connected finally. Just try to understand. Actor will try to predict an action. Critic will try to predict a value. Okay. And then we'll see in the final architecture how is this used for modifying the final neural network architecture. But critique is nothing but it predicts the value, and we will see how it is used. Just note this term. If you just want to write it down, write it down. Actor head simply predicts the action. Critic head simply predicts the V, which is V corresponding to a state S. Then, now what PPO is, in PPO, the actor-critic heads or actor and critic framework is part of PPO. PPO also has everything else that we discussed, but PPO has a few additional things. So one thing that happens is in naive grading, in naive upgradation of the this policy network, what was done was, if you followed this equation, right? The problem that was happening was, let's say there was one particular action at this current state which resulted in huge reward. Just think about that. Let's say there was one action which resulted in huge reward. What will happen is that action will result in a big AT, which is a big advantage. If AT is big, if the absolute magnitude of AT is big, the absolute magnitude of gradient of J is also big, which means if gradient of J is big, then the weights and bias parameters of the pi of the neural network will be modified a lot, which means the amount of change that is happening to your policy will change so much just because of one good action or just because of one bad action. Because if it's a bad action, also policy will change. So essentially, the policy upgradation is so noisy and it is so much dependent on the reward result, which results from one particular policy. So that was the problem with this noisy policy upgradation, was one problem with the naive reinforced based approach. And somehow PPO is solving that, which we should discuss. So just to reiterate, in naive approach, if a particular action resulted in huge reward or huge negative reward, it has a huge positive or negative influence on AT, right? Because AT is basically Q minus V. And if a reward corresponding to this step is very high, Q will be very high and vice versa, which means AT will be dependent on that. If AT is a huge or a very big number or very big negative number, this gradient is either very big positive number or very big negative number. As a result, the values of theta, which are the parameters of the neural network, will change so much. And when the values of the neural network change so much, what does it mean? Because those values represent the probability distribution of your policy from which you are sampling an action. Which means if those parameters are changing so much, your policy is changing so much just because of one particular action. So it's called as a noisy policy upgrade, which you don't want to do. You want it to be smoother. So what is done in PPO is something which prevents that. We will discuss that in a moment. Let me go back to the slide. So there is this concept of pi old and pi theta. Pi theta is, or pi new. We can call it as whatever, but pi old is what did the neural network look like before upgrading the parameters, meaning what did the policy look like before upgrading theta? That is pi old. Pi new is what did it look like after upgrading? Okay, these two terms are important because this is used for calculating one parameter. Just keep it in your mind. Now, in PPO, we keep a track of at every gradient step in neural network backward propagation. We look at how much different is the pi compared to pi old. Meaning, if we have a backward propagation upgrade which results in different weights and biases, how much is that neural network, how much is the probability distribution corresponding to that neural network different from the previous distribution? And we have discussed many times in this course, how do you compare two distributions? What is the function, or what is the way in which you compare two different distributions? KL divergence. And if KL divergence is high, is that a good thing or bad thing in this case? Because we are saying that the neural network should not drift so much, which means if KL divergence is very high, it means those two distributions, the current state of the neural network and the previous state of the neural network, are highly different. So you will see in one of the future slides, we introduce a KL divergence cutoff, saying if KL divergence is greater than like 0.03 or something, it means that the new policy is so much different from the old policy that we will not do that upgrade. We will only do the upgrade if the policy is changing only slightly. Okay. I'm so glad that you guys mentioned KL divergence. Very good. So just remember these terms. Yeah, it's a hard coding. Yeah, I mean, whether it's bad or not, for sure it's bad. I don't like the arbitrary usage of 0.03, but that's what people figured out is a good number. I'm sure there are other RL algorithms which have, or other papers which have found out better numbers. But yes, you will see one more hard-coded number. I'll show you that in a moment. But there is something called this importance ratio R, or RT, which is a function of theta, which is pi divided by pi old. Just ignore all of this AT, ST, etc. AT is action conditioned upon action followed by state. So R is nothing but the ratio of current policy divided by the old policy. Okay, and the current policy action, the ratio of the two pi's, which measures the drift. Now, if RT, the importance ratio is, let's say, very high, it means the current policy is so much higher than the previous policy. So this measures how much likely, or in a better way to put, for the given state, how much more likely is the new policy to favor the action AT compared to the previous one. Okay, this is not a very important term, although it's used in an equation. Just keep this in your mind. I'll finally come to the equation. So just taking 2 steps back, we discussed that reinforce algorithm, which was gradient of J is equal to sigma A multiplied by logarithm of policy. That was the gradient of J equation. It was too much dependent on the quality of individual actions. And because of that, the extent by which the policy was getting modified or the weights and biases in the neural network was getting modified was so much. It resulted in very noisy gradient update. We did not want that. And PPO tries to solve that. And to solve that, PPO keeps track of how much change is happening to the policy. So there is an old policy and new policy. And one way in which you can keep track of this is by having the KL divergence. So what PPO does is, it basically, this ratio, it tries to clip within a value between 0.8 and 1.2. So this is the other arbitrary number, just like the 0.03 KL divergence number. Basically, what it says is, if the if the probability with which a certain action is taken at a certain state on an average is more than 20, if the ratio is greater than 0.2, if ratio is greater than 0.2, it means there is 20% higher likelihood of picking an action at a particular state with the new policy than the old policy. Then that new policy is not taken into account. Or if the ratio is 0.8, 0.8 means roughly 20% less likelihood of picking a particular action for a particular state by the new policy compared with the old policy. That is also not considered. So basically what we are saying is, we are only allowing limited range of modifications to the policy. That is essentially what we are trying to say. Okay. So just keep that also into account. So now what PPO tries to optimize is the following. So now this is the equation. Okay. E stands for expectation. So PPO tries to find out the expectation of the minima of this versus this. So now what is this? R multiplied by A is, R is the this importance ratio multiplied by advantage at T. You know what? Let me just take a pause, because too many terms are introduced in this one particular slide. Let's take a step back and try to understand what we are doing. We somehow want to prevent the policy getting updated by so much in one single upgrading, in one single gradient step. Why do we want that? Because we should not have any one single action or a few number of actions having so much influence on how the policy is modified. So all of this, what we are trying to do is an attempt to make sure that the policy does not get modified randomly by a huge amount. Okay. We'll come back to this slide actually. Just remember this, what the objective of PPO, and this is called as PPO clip surrogate. So this surrogate is, it's a surrogate objective compared to the previous objective. What was the previous objective in reinforce? It was J of theta. J of theta was, the reinforce was trying to maximize the value of J of theta by finding the appropriate values for theta by performing backpropagation in the neural network. In PPO, it describes a surrogate objective which takes into account the importance ratio as well. Okay. This equation, no need to try to understand this right now, but just try to understand that in PPO, you are defining a slightly different objective to optimize. Then, so we'll come back to this, but let's look at the neural network architecture first. That will be a better thing to do. This slide basically just pictorially represents the 0.8 to 1.8 idea. And there is one more term, and I promise this is probably the last or second last term that we will discuss. It's called generalized advantage estimation. So basically, instead of picking the advantage AT as the difference between current Q and current value, a different formula is applied. So I'll just explain the formula. Yeah, so many terms. And this is just one part of RL, right? That's the reason why RL books are so hard to digest. It's like, if you sit down and start with any RL book, it's very mathematically heavy, and mainly because so many different ideas are there. And unless you spend a lot of time, it's very hard to put all of this into your brain at once. So that's why I mentioned in the beginning of the lecture itself that just the sheer number of terms itself is overwhelming, which is okay. You spend some time and you will get used to it. But just try to understand the overall idea. The overall idea is, how can I make the policy, which is a neural network, pick the right action so that my return is maximized. And in doing so, I have to keep upgrading the neural network through backward propagation. And that has to be as smooth as possible, right? So this generalized advantage estimation is nothing but it's a slightly better way to estimate the advantage by taking some of the future steps also into account. The formula is actually very easy to understand, but I don't intend to explain to you right now. The reason is if I also start explaining this, the amount of things that you have to store in your brain in today's lecture is too much. But the broad sense is instead of calculating the advantage as A equal to Q minus B, you follow slightly different approach. Just look at what is it doing. So this is called as like a delta. It's called TD residual. I think it's called temporal difference residual or something. TD stands for temporal difference. Delta is equal to current reward plus future value multiplied by a discount. So future value multiplied by a discount, because anything in the future we are discounting by the discounting factor gamma, which is like 0.99 or 0.9 or something, minus V times ST. So this is very similar to Q minus V. If you think about what this is, just think about what this is. This is not exactly Q, but it's somewhat resembling the Q. And can you tell why? Because RT is the specific reward corresponding to a specific action from the current time step. Gamma times V is, and when I take a specific action resulting in a specific reward, my state will change from ST to ST plus 1. And at ST plus 1, in that state, I have a value, state value. I can calculate a state value. That state value, however, because it's in future, I have to discount it by a factor of gamma. So now this whole term is like a alternative Q term. This V term was already there in the calculation of A. Then the generalized advantage estimation does a sequence of, you do a summation from sigma k equal to 0 to k equal to some time step, where you also have a additional discounting factor called lambda, which makes this generalized advantage estimate factor calculation smoother. But more than this, let us not go into it. It's too much. But just understand that what this is doing is calculating the advantage instead of calculating it in a naive way like Q minus V. It is also calculating the advantage by taking few more future steps into account. That's essentially what we are doing here. And it's called GA, Generalized Advantage Estimation, GAE. No, RT is dependent on an action. Yes, you are asking about the RT within the equation, right? Yeah. And there is, this is the last term. I think, let me just go back to one more slide ahead. Just make sure that that's the last term. Yeah, I promise that this is the last term, which is called as entropy bonus. Entropy bonus is simply, I told you that we have to, the action that is predicted by the policy is not deterministic, correct? So the policy is sampling from the action is sampled from a probability distribution. Yeah, good question, Pratik. Where does exploration versus exploitation come? Exactly here. So I told you that when we are sampling from a distribution, that distribution has a mu and sigma, correct? The policy is basically a probability distribution which has a mu and sigma. We don't want that sigma to be very high, very low. Why? If sigma is very low, your points which you are picking will always be close to mean, which means you will not do any exploration. You're always exploiting. But when you create a probability distribution, you want sigma to be somewhat higher. Then only the exploration will come into picture, because then the action will be not necessarily the perfect action for that particular state. It may pick a suboptimal action also. So how do you tell your neural network that, hey, you have to predict sigma, which is not too small? For that, what you do is you introduce a parameter called entropy, in which that sigma, which is the standard deviation of the Gaussian distribution, which is part of the policy, is there. So if this value of sigma is higher, the value of entropy is higher. Then what you do is this entropy will be part of your loss function with a negative multiplier. So basically what the final loss function will also the final loss will be lower for predicting a distribution with a lower sigma, meaning if your distribution has more variance, it is a good thing. The network loss will be lower. So you will prevent your network from predicting a distribution whose sigma, which is the standard deviation, is close to 0. I will show you exactly where that comes, but this is the last term, entropy. So now if we lay out all the terms that we have discussed, state, environment, action, reward, those were the first few terms. Behavior cloning versus reinforcement learning, that was another concept. Then we also discussed about deterministic policy versus stochastic policy. Then we discussed about state value versus action value. State value was V, action value was Q. Then we discussed about advantage, which was the difference between Q and V. Then after that, we looked at what are we trying to optimize in the reinforce algorithm. In the reinforce algorithm, we are trying to optimize J of theta, which is the return. We are trying to maximize it. So the gradient of J of theta was summation of product of A with the logarithm of pi, where A is the advantage and logarithm of pi is basically logarithm of pi for a specific action. Now, if a specific action resulted in a very high advantage, the gradient of J will be very high, which means the policy will get updated so much in dependence with that particular action, which is not a good thing, which is why PPO, Proximal Policy Optimization, is trying to modify the policy such that the new policy is in proximity with the old policy. That is why the word proximal is coming from. The new policy has to be within a certain proximity of the old policy. What is the policy? The policy is the neural network itself. What do we mean by optimization? We are trying to find the peak or maxima of that optimization, but we are trying to find it in a smooth way. We will never allow huge changes in policy in one round of backward propagation. That is why the word proximal is coming. And few more terms we discussed is generalized advantage estimation. Generalized advantage estimation is a different way to calculate the advantage by considering future discounted time steps also. Now we are also discussing entropy, where entropy is will come into picture in the loss function, because entropy is directly proportional to the sigma, which is the standard deviation of your distribution. And higher the sigma, higher the entropy, and higher the entropy, it will contribute negatively to the loss function, which I will show you. So basically the loss is reduced if there is a higher sigma, which is a good thing because that will promote exploration. We also discussed about KL divergence, because KL divergence is an index of how different two distributions are. So if pi old and pi new are very different, meaning if the KL divergence value is very high, it's not a good thing. Then also we will not allow any modification. We also discussed about the surrogate objective, which was there in PPO, surrogate objective, that L function, which we did not go into detail, but basically all we need to understand is that surrogate objective is different from the J of theta objective, which was used by reinforce. But surrogate objective also takes into account pi old and pi new, and whether the difference between those is less than 0.8 or greater than 1.2, it is not allowed. So these are the things which we have discussed so far. Now, with all of this, we will try to have a look at the architecture itself. So finally, this loss I will come to in a little bit. KL divergence also I have discussed, so no need to show the slide. Now let's look at the neural network architecture. Now, this is what we will be doing in this today's lecture, or rather after the today's lecture. You have the meta drive sky bridge. It's called sky bridge because the physics of it is set up in such a way that you will fall down if you go out of the bridge. Let me just open my VS Code and show that to you. Yes, reinforce would lead to large variation in policy. Exactly. That is the exact reason why we don't prefer reinforce. See, this is called the sky bridge. I hope you can see the GIF. And this is a very bad policy, by the way. The car is not finding the turn properly. But if it falls down, it's a terminal state. Okay, so this is the arena. It has to follow the track, follow the turn, and it has to reach the terminal state. That's the goal here. Then the environment is basically that meta drive sky bridge, but the view that the car is seeing is like a 94 by 94 pixel or something like that. It's like a vision model. So the only input that we are giving, we are not giving any other input. The only input the model is getting is the vision. We could use Isaac Lab also, of course. The only reason why I did not use Isaac Lab is it prevents many of you guys from actually trying it out. MetaDrive is free for all, so it's very easy, and MetaDrive allows you to collect a lot of parameters. That's the only reason. But technically, this can be done in Isaac Lab also for sure. So the environment will give you observation, which is the image which the car is seeing, the camera on the car is seeing. The reward RT is calculated based on bunch of parameters, based on how much is the throttle, whether the car is centered with respect to the road, etc. Right? So there is a complex reward function which I will show you afterwards. But reward function, I hope you can already imagine. Reward should be higher for driving fast. Reward should be higher for drive. It should be lower for driving fast in a corner. Reward should be higher for centering the car in the road. Reward should be higher for making progress along the road. Reward should be high if it reaches the endpoint. Right? So you can imagine a reward function. And in the homework, what you will be doing is you will be using your own custom reward function. And the goal is to make sure that your car reaches from start to finish in the minimum time as possible through the road. Okay, that is the end goal. Then based on this observation, which is the input, image input, you have an agent network. Agent network is nothing but a CNN. That CNN will produce an action. That action will be fed back into the environment, and environment will produce the next state, which results in the next observation. And there is a resulting reward. Then the neural network will again get that observation. It can predict the next action. So basically during inference, you just have the trained policy, which is the neural network. That trained policy will collect observation. It will perform action. It will collect observation and it will perform action. If you have more than one car, in principle, yes, it should work if there is more than one car. But then the thing is, if you want to do some sort of racing between different people with different policy, and if you want to win, because I think in MetaDrive collision physics is there, and if you really want to win, you have to train by having some additional cars also, and you have to have reward function which penalizes collision. In the current setup which I have only one car because it's the simplest setup. But if you want to have a setup where collision is avoided, overtaking a car is there, then reward, it has to reflect in the reward function. Otherwise, plus it has to also reflect in the state, because if the state sees no other car, how does it know what action to take? So you have to modify the environment such that multiple other agents, other cars are also there. So in inference, basically, it's very simple. There is a trained network which produces the action based on observation. That's it. But during training, what happens? During training, this network itself need to be optimized, right? If network itself need to be optimized, we need to calculate Q, we need to calculate V, we need to calculate A, then we need to calculate loss function, we need to calculate KL divergence, we need to calculate entropy. All of this is coming into picture in the final loss function. So what I'll do is, in the next few slides, we will jump into each of these individual items in detail. We look at the environment in detail, the policy neural network in detail, what this rollout buffer is, because nobody asked the question, how exactly are we going to calculate Q and V? Because Q and V depends on the future time steps. So if future time steps are required, and if I'm currently at the current time step, how exactly are we going to get the value of Q and V? Nobody asked that question. So we should discuss that also. We should discuss the loss function. We should discuss optimization, how exactly one loop of gradient descent looks like. And we should also discuss at the end what the reward function is. All right. So let's look at the first part. First part is, how do you get in what shape do you get the image? So image, we are taking last 4 frames, and they are stacked as three-dimensional, meaning RGB image. So there are 4 such images. The images are of size something like 92 by 92 or whatever you need. And there are convolution layers which convert this image, a single stack of 4 images, into a vector of 512 dimensions. How does it do that? Each convolution layer will shrink the spatial dimension and it will increase the Z stack dimension. And like that, if you pass through multiple convolution layers, and then after that, if you do a projection, you can finally get a 512 dimensional vector corresponding to an input, which is the current frame plus the past 3 frames. Okay. So this image is finally converted into one single vector through a sequence of convolution layers. That is the first. So this sister figure 1 corresponds to what happens um, uh, from the environment to the agent. Now the agent network itself will look something like this. So the agent network itself, when I say agent, I mean the policy agent. It has to predict two things. It has to predict an action, and it has to predict a value also. So, I already discussed this. So this and this has two specific names. This linear plus tan h, which outputs the action, and this thing which outputs something. I will not tell what that is. There was some name for these two things. What was that? It was actor and critic. So actor predicts the action, critic predicts the value v, right? Actually, v is not my bad. V is critic is not shown here. Critic should be shown in one more box, but after the input, which is the image converted into 512 dimensional vector, you predict action and you predict the v. Now in the action, in our case, how many actions do we need to predict? What is the dimensionality of the action? Is it 1? Is it 2? Is it 512? Is it 4? What is it? We already discussed action. There is only two actions. There is throttle and there is steering. In our current example, in the meta drive. In the previous examples, if it was the simple 3JS based simulation platform which we use, there were 4 actions: VX, VY, forward, backward, left, and right. If it was TurboPy, it had VX, VY, and omega. In our case, there are only 2 actions: the steering position and the throttle. Okay. Now, is the model predicting the action directly? No, it is not predicting the action directly. It is predicting mu corresponding to action number 1, mu corresponding to action number 2, sigma corresponding to action number 1, and sigma corresponding to action number 2. What is action number 1? Action number 1. Action number 1 is steer. Action number 2 is throttle. Because there are two things, right? You have to orient the angle of the steering and you have to put the throttle. So for steer and throttle, you predict mu and sigma. What does it mean when you have a steering related mu and steering related sigma? It means the value of how much your steer is can be sampled from a distribution whose mean is mu and whose standard deviation is sigma. So you can construct a normal distribution based on the predicted mu and predicted sigma corresponding to steer. Similarly, you can construct a normal distribution whose mean is mu and standard deviation is sigma corresponding to the throttle. So there are 2 blocks here. One block predicts the mean of the outputs, mean of the actions, which is mean of steer and mean of throttle. Another block predicts the standard deviation, which is sigma of the steer and sigma of the throttle. Now, using the mean and sigma, then so that totally there will be 2 means and 2 sigmas. One mean for constructing the steering normal distribution, one mean for constructing throttle normal distribution, one sigma for defining the spread of the steering, one sigma for defining the spread of the throttle. And from that normal distribution, and now we'll have 2 normal distributions. From the first normal distribution, when we sample something, what do we get? We get a predicted mean. From the second normal distribution, when not predicted mean, predicted steer. And when we sample from the second normal distribution, we get the predicted throttle. So that is how finally you get the raw values of throttle and steer. You don't directly predict it. None of the network directly predicts it. It predicts the distribution. From the distribution, you sample randomly. And then there is one step where raw values of raw values of steer and throttle are converted to -1 to +1 range using a tan hyperbolic function. Because it's better if the outputs are in a normalized -1 to 1 range. And then this is the final action that is fed into the environment, because finally, whatever action the model is predicting, it has to be fed back into the environment to get the new image or the new state. Then that state is again fed back into the neural network and it predicts the new mu and sigma. Using the new mu and sigma, you sample to get the new steering and throttle. Then that new steer and throttle again is normalized using tan hyperbolic function to -1 and 1. Then it is again passed back into the environment to get the new, to implement the new action and to get the new reward and to find the new state. This is applied recursively until you reach a terminal state. And that you can call as maybe one episode, right? And this, I'm talking about inference right now. Training will be same thing, but doing back propagation. One small thing you have to notice is that when action is being applied in the environment, there might be a scaling factor, because the actions in the environment might depend on in meta drive, is it expecting values in the range of 50 to 100? Because then you can't pass -1 to 1, minus this normalized range into meta drive. So before this action is being applied into meta drive, there will be a scaling factor so that this action is fitting in that environment. Okay. So this sigma, now people were asking where is the exploration coming into picture? It comes into picture because of this sigma, because if sigma is high, then when you are sampling from this distribution, the variance in values, even for the same exact state, can be very high. And based on that will come the concept of exploration. Exploitation will be the case where sigma is very, very low. If you don't want exploration, just sample directly at the mean. If you pick from here, you will always pick the highest probable outcome. And then entropy H is calculated from, okay, Sandeep, why tan H in between? Why can't we scale directly after picking a value from the normal distribution? Because when we are training the neural network, in general, if you look at the parameters within the neural network, it's better if they are confined within a certain value. On the other hand, if mu and sigma, because ideally this mu and sigma distribution, it can have very big values, right? The steering value, it theoretically goes from -infinity to infinity. So you can't have such very, very big values. Okay, there is one more quick question. Why Gaussian distribution? So if you really want to create a probability distribution for sampling just one parameter, Gaussian distribution is the simplest, and it's an approximation. Just like in diffusion models, we are approximating that the probability distribution of, let's say, your data point is Gaussian with a mu of 0 and standard deviation is 1, right? So normal distribution is basically an approximation for how the actual set of actions may lie in that space. The actual distribution might be slightly different, but this we are taking an approximation. All right, so this is the action part, how the action is coming into picture. Now let's discuss about the critic head, because this is the actor head, right? Actually, technically, these two are actor head. This was not the critic head. For a quick time being, I thought this was critic. No, these two are actors. It's just two heads which are predicting mu and standard deviation separately. Now let's look at the critic head. Critic head will get the exact same input which the actor head is getting. So they are both in parallel. So if this is a 512 dimensional vector, critic head will also get a 512 dimensional vector. And critic head will predict V, which is the state value. And this state value is used at two different places. One, it is used for calculating a loss. And what is that loss? Loss is the predicted value of the state versus actual value of state. So difference between that. And it's also used in generalized advantage estimation, in the generalized advantage estimation formula. Now, one question you should ask me is, okay, we understand how a neural network can predict a number, because neural network, if it is trained, it can predict any number. But where is the ground truth value of V coming from? Can anyone answer? My question is, we always keep talking about V and S and advantage and G. But in all of these cases, we need, if we want to calculate GT, I need RT, RT plus 1, RT plus 2, RT plus 3, etc. But if you look at what we are doing, we are still at time T. So how do we know RT plus 1? How do I know RT plus 2, RT plus 3, etc.? Like, how do I know the future states, rewards, etc.? And how do I know ground truth value of the state value? Because this critic is predicting a value V for sure. But then if I'm comparing it with an actual value of V, somewhere the actual value of V has to be already available, right? Otherwise, how do I compare? So what is done is something called as, yes, multiple episodes. Yes, that is a great way to put it. Basically, what is done is a large number of episodes are played out and a buffer is created. Yes, it is calculated. I'll just show you that buffer image. So what is done is there is something called a rollout buffer. And one buffer is corresponding to one pi or one policy. That buffer, what it does is it picks a fixed number of time steps, okay? And for that many number of time steps, it will roll out a bunch of actions. So at current state, let's say it is 0.04, 0.05, etc. Just some number representing the state, and there are corresponding actions to that state. And the policy is the same policy. This is corresponding to the same policy, and there will be corresponding rewards at every single time step, and there will be corresponding VT calculate, because now if you have this entire table available, if you have all of these columns available, you can calculate VT just like how you will calculate like a cumulative sum or something in an Excel sheet. So you can have VT, because VT is nothing but the value for the current state, which is the expectation value of the return for a corresponding state. And then you can also calculate QT for a given action, right? So this rollout buffer is basically a pre-calculated table for a given policy. And using this pre-calculated table, and it changes at each and every time when the policy is modified, because when the policy is modified and policy becomes pi new, this table is not valid anymore. Then this table has to be regenerated. But this table is calculated, and that table gives you ground truth values for VT. Okay. So that ground truth value of VT is compared against the predicted value of V in the critic. And this is one of the loss terms. So there is one loss resulting from the PPO loss, one loss resulting from the actor-critic loss. Then there will be one loss term due to the entropy related loss. Okay. Now let's look at the one last thing. This generalized advantage estimation. Generalized advantage estimation, basically I told you like it has to involve future time steps also, because the original advantage estimation was simply Q minus V. Generalized advantage estimation involves a lot more future time step calculation. But this is also again calculated based on the rollout buffer data, because if you want anything from the future, you look at the buffer data. And that is dependent on current pi. When the pi is modified, rollout buffer data is also modified. Yeah, now this is the final PPO loss function. The first is the surrogate clip loss, which is what we discussed saying. It's slightly different from the J of theta, where here you are trying to make sure that the modification between new pi and old pi is between either 0.8 to 1.2, the reward. And the ratio between pi old and pi new is it should not be greater than certain percentage. So this loss basically takes care of that. The second loss is the critic loss. Critic loss corresponding to the value predicted by the critic. The third loss is now, this is the negative term which I mentioned. Third loss is the entropy related loss, which the entropy is multiplied by a negative number. Can anyone tell me why this negative number multiplication is there with entropy? Why are we having this negative number here in the entropy bonus? It's also called as a bonus. It's not called as a loss. Why is that? Because as we said, why are we even introducing this in the first place? The reason why we are introducing this is we need to have sigma that is not too small. If sigma is too small, then there is no variance. You need a sigma that is somewhat high, and entropy is directly correlated with that sigma, which means if entropy is high, the network is kind of doing a good thing to have variance. And if network is doing a good thing, you should not penalize the network, meaning the loss should be somehow minimized. So if H is positive and big number, and if you multiply it with a small negative number, you get an overall H term, which is a small negative number. And if a small negative number is added to the loss, it means the overall loss is decreased, right? Which means you are less penalizing the model now, or you are kind of rewarding the model now for predicting sigma that is kind of high. That is essentially, I mean, not too high. If it is too high, also it's not good, but it kind of incentivizes the model to predict sigma that is not too low. That is the PPO loss. Okay, this we already discussed, the KL divergence part. KL divergence is if the new network and old network is differing in KL divergence by greater than 0.03, you don't modify the policy. And this is the rollout buffer. And I think, and this one figure captures, I couldn't make a better version of it, but this one figure captures everything that we discussed so far. So the observation is the RGB frames. There are four stacked frames. This is the RGB, and this is the X and Y resolution. Then through 3 convolution layers, finally it becomes a 512 dimensional vector. That 512 dimensional vector goes as the input into both the actor head and critic head. Actor head will convert the 512 dimensional number into 2-dimensional number. Why 2-dimensional? Because there are 2 actions, steer and throttle. And this actor head actually has 2 subheads, one head for predicting mu, one subhead for predicting sigma. And based on the mu and sigma, you sample from the distribution. So that is this. So pi theta of state is normal distribution based on mu and sigma. And the entropy is calculated from this sigma. And from this pi, you sample, then you squash. What do you mean by squash? Squash meaning you normalize it between -1 to 1 through tan hyperbolic function. Then after normalization, before you apply it into your environment, you apply a scaling factor because environment might require different scaling. So this is where the scaling applies. And then if you apply the scaled action in the environment, then the environment will give you some new reward and new state. And to compare, now in the loss function, we have to compare the H, we have to calculate the surrogate loss. We also have to calculate the loss due to critic. So these 3 losses we need to calculate. So those losses for calculating, you will use the rollout buffer. And how is rollout buffer calculated in the first place? Rollout buffer is calculated by performing a future horizon calculation, where future horizon may be 512 steps. And is the rollout buffer constant throughout the training? No. Rollout buffer will be modified when pi is modified. Okay. And yeah, so then I think rest of the things are fine. Generalized advantage estimate we discussed. Entropy bonus we discussed. Value loss we discussed. So value loss is the loss due to critic. Entropy loss is the loss due to entropy. Then clip surrogate is basically the PPO loss or PPO surrogate loss. Then yeah, this was another condition. The KL divergence should be less than 0.03. And importance ratio has to be within a threshold. So that also we discussed. And yeah, and what is done is the model is, and when we say model, where are the model parameters, by the way? Where are they residing? Can you tell me exactly where the model parameters are residing, where the policy parameters are residing? Out of what you see here, where all are those parameters residing? In this case, it's primarily, I mean, you can say it is in 2 places, but it's primarily in 1 place. It's in this linear projection from 512 to 2. That has to be done for mu and standard deviation. Then there is another 512,1. Oh, by the way, why is this 512,1? Because critic head is only predicting one thing. It is only predicting value. So there will be 512 weights here, weights and bias parameters here. There will be 512 times 2 plus 2, that many weights and bias parameters here. And if you consider that the CNN encoder is not really trained to encode the information into a 512 dimensional vector, meaning if you are not using any pre-trained CNN encoder, then all these parameters are also now updated. So now primarily the parameters which influence your pi, which is the policy, will include the CNN encoder parameters, the actor head parameters, and the critic head parameters. So your policy is primarily the actor head parameters for sure. But if CNN was not at all trained, you can say as the policy is getting better, CNN parameters are also getting updated. So if you look at where the brain is, where the policy is residing, it's in the CNN plus actor head plus critic head. Okay, I think that is mostly what I wanted to discuss regarding the whole PPO architecture. Now I'll tell you what you are supposed to do once you go home. Okay. So there is this GitHub repo, which I want to share with you. Let me just find it 1 second. So now what I want you to do is the following. So with the help of Naman, we have created a website, and this website is basically like an arena where you can perform racing car training using the PPO policy. What you have to custom define is your own reward. And at the end of the day, you will have to get a policy trained and so that it can actually perform an action. Our policy, I have not deployed the train policy here, but to train it to reach a certain baseline performance, you have to train it on CPU for at least 3 to 5 hours minimum. So what I recommend is if you have access to RunPod, use RunPod because then it will be much faster and you can try a lot more things. And the GitHub repo corresponding to this, with all the instructions you can find, if you click this GitHub, it has all the instructions on what exactly to do. So all you need to do is you can use Cloud Code or Codex to execute the commands, or you can directly execute this in the terminal. It will clone the repo and it will basically perform the training part. What you have to custom define is the reward, because if you don't change the reward, nothing is going to change. Like the performance between two people is not going to become better or worse. It will be more or less the same. So try to identify smarter reward function. So this reward config.py is where a bunch of reward parameters are there. If you want to introduce additional parameters, that also you can do. But what it will result in will be a final reward function, which will look like this. So my final reward function, which is the current default one, is like this. There is a reward for progress meaning moving forward. There is a reward for centering the car. There is a reward for heading meaning car facing the curvature of the road perfectly. There is a reward for following a certain speed. There is a reward for control, meaning random idling, random braking, etc. will involve penalty. There is reward for reaching the terminal state or bonus for reaching the terminal state. And all of this constitute the reward. And this is a big function which is written in the reward config.py. And where is this reward calculated and where is it coming into picture in the neural network? It is coming into picture over here. Over here. So when the environment, when you're predicting an action, performing a particular action implementation in the environment will produce the reward, and that reward will be again part of the calculation of V, calculation of Q, and calculation of the surrogate loss component within PPO, right? So that is where it is coming into picture. But at the end of the day, the way you define the reward is what is going to differentiate your performance from someone else's performance. So spend most amount of time on that. If you want to clone the repo and modify something massively, like if you want to even change PPO and use some other RL policy, feel free to do that. But for a fair apples to apples comparison, try following PPO. The instructions for submission is mentioned here, but if you want more details, I can share that also. How do we define the rewards, and is it scalable if we define the reward manually? I have no idea how Wave AI is doing it, but defining reward manually, ideally the reward, there should be a neural network which can predict a reward or predict a value which is similar to a reward function. In complex environments, defining reward manually is very difficult. You remember in world models lecture, we had a neural network which was not just dreaming the trajectory, but it was also predicting the reward, right? So we have to have a neural network which predicts some sort of reward. But at the end of the day, a lot of manual work has to be there in defining the reward, because only humans know what we want. We know what we want. We know that the car has to drive in a certain way. Otherwise, we are not happy. If we are playing the game, we know that the game has to be played in a certain way. Otherwise, we are not happy. So a huge component of the reward function is human defined. But in real world, the reason why it becomes complex is then we'll have infinite combinations of reward and penalty to define, right? So there a basic reward function will have a huge component of manually defined terms, but remaining will be predicted by a neural network. But I think this is a good place to wind up the lecture. And this is the second last lecture of the VLA for autonomous driving series. In the next lecture, what I'll show you is something fairly new and interesting, which is using agent as a policy, using coding agent as a policy. It's not tried out that much in literature. Very few papers are there, but it's coming out as a new concept. The concept is this: instead of using a huge trained model, like a world model, because the agents are already inherently good at doing things, can the agent directly come up with motor commands in one shot by looking at what is seen through the camera and by basically observing the environment? Can an agent do this? It is slow, we know that. I mean, of course, for agent to process it and produce an output, the latency is much higher than the latency of world model or latency of VLA models, or I mean, pi zero. Of course, that is true. But I think eventually this idea will come into some sort of physical manifestation, because agents are already good at doing most of digital tasks. If you think about all the digital tasks, agent can do it already really good for you. So agent can, in principle, be also good at physical tasks, which involve looking at the environment, calibrating to make sure that the geography and the physics are matching, and then in one shot predicting what to do, something like that. So it's in a very nascent stage. The field is in a very nascent stage, but I think in our bootcamp we can discuss it because it's a lot of fun. Also, using agent as a policy is very much fun. So let's do that. Repeat the agenda. Yeah, the title is basically using agent as a policy instead of using a trained. So here we are using a trained model as a policy. Instead of that, use agent itself as the policy. Can agent come up with motor commands to execute the action? That's the idea. So we'll discuss that in the next lecture, which will be the last lecture. So thank you, everyone. I know that in this lecture, we have discussed at least maybe a couple of dozen terms. It's very mathematically involved. So please rewatch it, take down very good notes, read from different sources of internet, look at ChatGPT, ask about definitions, and try to understand the interconnections. It's not hard to understand. It's just that it takes time. So you have to spend time on PPO to understand it properly. Yeah, O'Reilly book, I have tried it. It's okay. I mean, if you have time and patience, it's okay, but you will require a lot of attention. Like you will have to spend a lot of deep work sessions for sure. But otherwise, thank you so much, everyone. We will meet in the next lecture. Please continue your discussions on Discord, and please rewatch the lecture as many times as you want. Please take good notes. And if anyone managed to make very good notes in whatever format, doesn't matter, do share it with everyone on the Discord. Like let others also benefit from your notes. When I say notes, I don't necessarily mean handwritten notes. It can be in a compiled PDF format, anything, any format. But if you condense all these ideas into some nice format, do feel free to share it. Thank you so much. Let's meet again next week, and we'll wind up the whole series with that. See you soon.